Today we will be looking at 4.5, which is dealing with exponential and logarithmic equations. So, the property of log states that if x is greater than 0, y is greater than 0, a is greater than 0, and a is not equal to 1, we have the following. So, we could have numbers x equal to y, and that is equivalent to log base ax, and that's going to be equal to log base ay. Additionally, you could have the natural log base of ax, and that could be equal to the natural log base a and then y. So let's go ahead and look at this first example, solving exponential equations. So it asks us in this case to solve 8 raised to the x, and it's going to be equal to 21, and we want to give our solution to the nearest thousand. So the first thing I'm going to do is go ahead and rewrite the original problem. So we want to go ahead and take advantage of the property of logarithms, and that states that we can go ahead and take the natural log of both sides, or we could just take the log of both sides. So in this case, let's go ahead and take the natural log of both sides. So we will be left with natural log of 8 raised to the x, and that's going to be equal to the natural log of 21. So now that we've used our property of logs, what we can do now is try to get this exponent of an x out into the front. And the way that we can do that is use our power property. So power property, we can go ahead and take the x, bring it out in front, and that's going to leave us with the following. So in order to isolate our x here, we can go ahead and divide by the natural log of 8 on both sides. So that should get us x is equal to the natural log of 21 divided by the natural log of 8. And we can simply punch this into our calculator using the natural log button. So natural log of 21 divided by natural log of 8. That is going to get us an x equal to 1.464. Okay. So one thing that I quickly want to note is that the natural log of 12 divided by the natural log of 7 is not going to be the same thing as the natural log and then having a fraction of 12/7. So let's go ahead and look at our second example here. So we add a little bit more complexity to the equation here. We will have solve 5 raised to the 2x minus 3, and that is going to be equal to 8 raised to the x plus 1. So let's go ahead and try to figure out what this equation solves to. So again, I'm going to go ahead and rewrite our original here. And that is going to be equal to 8 raised to the x plus 1. So the first thing we want to go ahead and do, again, we see that we have some exponents and we want to go ahead and try to get them down. So the first thing we need to do in order for that to occur is use our property of logs so that we have log on both sides. So property of logs. So again, let's go ahead and take the natural log. Again, you could take the log of both sides. So natural log of 5 raised to the 2x minus 3. And that is going to be equal to the natural log of 8 raised to the x plus 1. Again, we had to satisfy that requirement of having the log so that we can take advantage of our next step, which is the power property. So using our power property, again, these exponents are going to come down in the front. So exponents down in the front. And what does that leave us with? It leaves us with 2x minus 3 natural log of 5 equal to x plus 1 and the natural log of 8. So now we can go ahead and try to see if any of this will simplify out. So let's go ahead and multiply. So the 2x times the natural log of 5 will get me 2x natural log 5 minus the 3 times the natural log 5 will get me 3 natural log 5, and that's going to be equal to x times the natural log of 8, so x natural log 8, and then finally plus the 1 times the natural log of 8, or in our case just a positive natural log of 8. Now the next step that we want to go ahead and do is see if we can get our x's on one side and our y's on the other side. So let's go ahead and add this positive 3 natural log 5 over to our right hand side. And additionally, we can go ahead and try to move that x natural log of 8 to our left hand side. So minus x natural log 8 minus x natural log 8. So what does that leave us with? It will leave us with a positive 2x natural log of 5 minus an x natural log 8. And this will be on our right hand side a 3 natural log 5 plus a positive natural log 8. So now we have our x's and our constants onto one side of the equation. So let's go ahead and try to pull an x out on our left hand side. So pulling an x out on our left hand side, we should get an x and then a 2 natural log of 5 minus a natural log of 8. And that's going to be equal to a 3 natural log of 5 plus a natural log of 8. So now all we need to do in order to solve for that x is go ahead and divide by 2 natural log of 5 minus natural log of 8, and then do the same on our right hand side. So 2 natural log of 5 minus the natural log of 8. So we can go ahead and punch that into our calculator. So we want to make sure to use parentheses. So the top portion will be 3 natural log of 5 plus natural log of 8 divided by 2 natural log of 5 minus the natural log of 8. So if we punch that into our calculator, we should get that x is equal to 6.062. Okay, so now we can go ahead and look at solving base E exponential equations. So solving base E exponential equations, what do we have for our first example? Well, we have e raised to the absolute value of x, and that's going to be equal to 50. So let's go ahead and again try to use that property of logs to get a natural log or a log on both sides. So let's rewrite our original here. And again, we're going to use the property of logs so that we can go ahead and get our exponents down. So in this case, natural log e raised to the absolute value of x is going to be equal to the natural log of 50. So now we can go ahead and use our power property. So power property here, and bring the absolute value of x down. So absolute value of x, and then we have the natural log of e, and that's going to be equal natural log of 50. So an interesting part that happens is that this natural log of e, so natural log of e is actually going to be 1. So what are we left with? Well, if that's just 1, we have the absolute value of x equal to the natural log of 50. So in this case, what we would actually have is x could be equal to plus or minus, in this case, the natural log of 50 turns out to be approximately 3.912. Okay, so now we can go ahead and look at our next problem here. So we want to go ahead and solve e raised to the 4x times e raised to the x minus 1, and that's going to be equal to 5e. So we have to actually use one of our properties previously. So we want to use the fact that a raised to the m times a raised to the n is actually equal to a raised to the m plus n. So see how we have, in a sense, the a raised to the m here, and we have the a raised to the n, and we can combine these and form a raised to the m plus n. So let's go ahead and see what that gives us. So we have e to the 4x plus, in this case, we will have x minus 1. So we can go ahead and take e raised to the 4x, and then we can go ahead and add that x minus 1. And that's going to be equal to 5e. And now we can go ahead and perform the necessary steps that we need to do. So the first thing that we can do is go ahead and combine. So this will give us e raised to the 5x minus 1. All I did was go ahead and combine these x's up here, and that's going to be equal to a 5e. Now, let's go ahead and divide by e. So divide by e. So that will give us e raised to the 5x minus 1 is equal to 5e. If we divide by this e here, and what this should give us is e raised to the 5x minus 2, and that is going to be equal to a 5e. And the reason I divided by an e here is because I saw that we had a 5e on the right hand side, and I want to go ahead and get rid of it. So in other words, we have e raised to the 5x minus 1 times, and since we divided by that e, really we could write that as e to the negative 1. So that's why it becomes e raised to the 5x minus 2. So now we are at a point where we can go ahead and use our property of logs. So let's go ahead and use our property of logs in order to get those exponents down. So in this case, let's go ahead and write it off to the side here. So using our property of logs, we will get the natural log of e raised to the 5x minus 2, and that's going to be equal to the natural log of 5. Now we can go ahead and bring those exponents down. So our exponent in this case is that 5x minus 2. So what will that give us? A 5x minus 2 times the natural log of e, and that's going to be equal to the natural log of 5. And if you recall, the natural log of e, again, you can try this in your calculator, it's going to be equal to 1. So we are left with 5x minus a 2, and that is equal to the natural log of 5. So all that we need to do now is go ahead and add that 2 over to our right hand side. So in other words, 5x is equal to the natural log of 5 plus 2, and then go ahead and divide by 5. So dividing by 5, you should get an x value equal to 0.722. Okay, so now we can go ahead and look at this other example here. So our other example asks us to solve for natural log of x equal to 36. So the first thing we see in this case is that we have a 4 on our left hand side. So let's go ahead and divide by 4. So that will get us the natural log of x is equal to a 36 divided by 4 will get us a 9. So now let's go ahead and try to rewrite this. So let's go rewrite. So the natural log of x equal to 9. So natural log of x, we can actually rewrite that as log base e. So natural log of x can be rewritten as the log base of e. And we have log base e and then x equal to 9. Well, now we're at a point where we can go ahead and rewrite in exponential form. So exponential form. Exponential form says that we go ahead and take our base, which is e, and then we take our exponent, which is 9, and set it equal to, in this case, an x. So e to the 9 is equal to x. Again, our base was e, our exponent is 9, and that's going to be equal to x. All right, so let's look at another example here. So we have a log base of 3 and then x to the third minus 5, and that is equal to 1. So let's go ahead and see if we can rewrite this in exponential form to create some sort of equation that's a little bit easier for us to solve. So again, we have a base of 3 and an exponent of 1 equal to x raised to the third minus 5. So a base of 3, exponent of 1 equal to x raised to the third minus 5. So first things first, let's go ahead and add that 5 over to the left hand side. So that will give us a 3 plus a 5, or an 8, equal to x raised to the third. Now, if we want to isolate x, all we need to do is take the cubed root of both sides, leaving us with x is equal to a positive 2. And we should be complete for that specific example. So let's look at our second one here. We have a log and then 2x plus 1 and then finally plus log x equal to log x plus 8. So the first thing we notice is that we have a plus here and we have our logs. So let's go ahead and try to use our product property to create something more useful here. So let's go ahead and use our product property. So our product property, we can go ahead and combine these. So that will be a log and then a 2x plus a 1, and then we are going back to our form so we can multiply it in that case. So now we can go ahead and use our property of logs, and instead of adding them, notice how we have logs on both sides, we can actually take them away. So that will give us a 2x plus a 1 times an x equal to an x plus an 8. So now we solve it like any other equation at this point. So 2x times the x and the 1 times the x gets me a 2x squared plus an x equal to an x plus an 8. So subtract the x's and you're left with 2x squared equal to 8. Divide by the 2, divide by the 2, and you are left with x squared is equal to, in this case, a positive 4. So take the square root of both sides, and you're left with x is equal to, and whenever you take the square root, you want to go ahead and have a plus or minus. So plus or minus 2. So at this point, we see that we have x is equal to a positive 2 and x is equal to a negative 2. We cannot actually use that negative 2 as one of our solutions, and the reason is that we would have a negative argument for this portion of our equation. In the first portion, we would have a 2 times a negative 2, which would be a negative 4, plus a 1, which would be a negative 3. So again, that would make one of the arguments for our log be negative, and we don't necessarily want that. So that is the reason why, in this case, we will just have x is equal to 2, not negative 2. So we can go ahead and look at some more examples here. So this example asks us to solve log base of 3, and then parentheses 4x plus 1 times x plus 1 is equal to a 3. So let's go ahead and try to rewrite this in exponential form to see if that will benefit us. So again, we are dealing with a base of 3, an exponent of 3, and that's going to be equal to our 4x plus 1 times x plus 1. So 3 raised to the 3 is going to give me a 4x plus 1 times an x plus 1. So now all we need to do is go ahead and multiply our right hand side out to solve for our x. So this will give us a 27 equal to 4x squared, and then finally plus 4x, so plus 4x, and then we will have plus x, and then finally plus a 1. So plus x and plus a 1. So this will give us a 4x squared plus a 5x if we combine our x's, and then finally let's go ahead and subtract the 27 over to our right hand side, so minus 27, and that would actually be equal to 0. So let's go ahead and try to factor this out. The 4 times the negative 27 gets us a number of a negative 104. So we want two numbers that multiply to negative 104, and added or subtracted together gets us this positive 5. So in this case, numbers that will satisfy these requirements will be a positive 13 as well as a negative 8. So further reducing, we will be left with a positive 4x plus a 13 multiplied by, if we take out the 4, we are left with an x minus a 2. And we can go ahead and try to solve these for x. So set 4x plus 13 equal to 0. And you're left with x is equal to a negative 13 fourths. And finally, x is equal to a positive 2. Okay, so let's go ahead and check our bounds. In this case, we will have a negative 13 divided by 4. If we plug it back into our original here, so plug it back in, we will have a 4 times a negative 13 divided by 4 plus a 1, which will give us a negative value times a negative 13 divided by 4 plus a 1, which is also a negative value. So a negative times a negative will actually give us a positive in this case. So the x is equal to 2. That again will give us positive arguments. So in this case, it is safe to say we have both of these as solutions. Again, just because it is a negative doesn't mean you exclude it right away. You have to go ahead and check to make sure when you plug it into your logs, if you get a positive number, you're good to go. Now, if you get a negative number, then you have to go ahead and exclude whatever that x is equal to. So let's go ahead and continue and look at our next example, which is log base of 2 times, in this case, 2x minus 5 plus log base 2 and then x minus 3, and that is going to be equal to a positive 3. So let's go ahead and try to solve this one. Again, we notice that we can go ahead and use our product property here. So using our product property, let's go ahead and simplify. So that will give us a log base of 2, and then we have a 2x minus a 5 multiplied by an x minus 3, and that is going to be equal to a 3. So let's go ahead and rewrite in exponential form now. So exponential form. So our exponential form, we have a base of 2, an exponent of 3, and it's going to be equal to this 2x minus 5 times the x minus 3. So base of 2, exponent of 3, and that's going to be equal to a 2x minus 5 times an x minus a 3. So all we need to do now is go ahead and multiply our right hand side out. So this gives us an 8 is equal to a 2x squared minus a 6x minus a 5x, and then finally plus a 15. So this will get us an 8 equal to 2x squared minus 11x, and then finally plus a 15. Now let's go ahead and subtract that 8 over and see if we can factor this out. So that gives us 2x squared minus 11x, and then finally plus a 7. And this is going to be equal to 0. So if we look at this one, normally we would say, okay, we need two numbers that multiply to a positive 14, and added or subtracted gets us this negative 11. But there really aren't any numbers that we can do that would be whole numbers. So let's go ahead and use our quadratic equation. So using our quadratic equation, this will be an A, this will be B, and finally that will be a C. So our quadratic equation here, we will have an 11 plus or minus the square root of negative 11 squared minus 4 times 2 and multiplied by a 7. Then we take all of that and divide it by 2a, or 2 times 2. And this should produce a positive 11 plus or minus the square root of 65 divided by a 4. Or in other words, 4.766 or 0.7344. So again, we need to go ahead and check to make sure that we don't have any negatives in our log arguments. So let's go ahead and check. So again, we want to go ahead and plug these values back into our original and check to make sure that there are no negative arguments for our logs. So you'd plug it in right there. All right, let's go ahead and check our arguments real quick. So in this case, we will have log base of 2 and then a 2 times a 4.766 and then finally minus 5. So what that would give us is approximately a 4.532, which is greater than 0, so we are good for that first one. And then we can add log base 2 and then 4.766 minus 3. And what this is actually going to get us is a 1.766, which is greater than 0. So again, we are good to go. So that means that 4.766 is going to be one of our solutions. Now we need to go ahead and check the 0.7344 to make sure that we don't have any negative arguments for our log. So log base of 2 will give us a 2 times a 0.7344, and then finally minus a 5. Now what this actually turns out to be is a negative 3.5312, which is not greater than 0. So we have negative arguments for our log. So just because this one is a positive does not mean it is going to be included. So we can go ahead and X that one out. So we just have the positive 4.766 in this example. Or if you want to, you could say the 11 plus the square root of 65 divided by 4. Okay, so let's go ahead and look at solving a base E logarithmic equation. So solving a base E logarithmic equation, first thing we see is that we have some natural logs. So we can go ahead and use our power property to bring that natural log of x out in front. So power property, let's go ahead and take the natural log of x and bring it out in the front. So natural log of x, natural log of e, minus natural log of x minus 4 is equal to a natural log of 5. So if you recall, natural log of e is actually equal to 1. So 1 times natural log of x is just going to be equal to a natural log of x. And then minus the natural log of x minus 4 is equal to the natural log of 5. So again, we need to go ahead and use one of our properties. So we see that we have the natural log of x minus 4, and we have the natural log of x, and we have a subtraction symbol in between. So let's go ahead and use our quotient property here. So that will get us a natural log of an x divided by an x minus 4. And that is equal to the natural log of 5. So now we can go ahead and use our property of logs. Again, we can use it to bring in some logs, or we can use it to take away logs. So since we have natural log on both sides, let's go ahead and take away our logs here. So that leaves us with an x divided by an x minus 4 equal to a 5. So all we need to do now is multiply that x minus 4 out from the bottom. And that leaves us with an x is equal to, multiply the 5 times the x, so 5x, and the 5 times the negative 4, or a negative 20. So let's go ahead and try to solve for x here. So that gets us, in this case, we want to go ahead and subtract the 5x. So negative 4x is equal to a negative 20. Divide by negative 4, divide by negative 4. Or in other words, x is equal to a positive 5. And again, if we double check ourselves here, that will give us positive arguments for our logs here, so we are good to go. Okay, so our last example here is going to be solving a specific equation for a desired variable. So in this case, we're going to go ahead and look at Newton's law of cooling. So T is equal to T naught plus C E and then raised to the negative KT. And we want to go ahead and try to solve for our K here. So let's go ahead and try to solve for K. First, write out your original. So T is equal to T naught plus C E raised to the negative KT. So first subtract your T naught here, because we want to go ahead and try to isolate that K. So we have T minus T naught, and that's going to be equal to C, E, and then finally raised to the KT. So again, we want to go ahead and try to isolate that K. So divide by your C here. So that leaves us with T minus T naught divided by C. and that's now equal to e raised to the negative kt. Now we can go ahead and take advantage of the property of logs and go ahead and take the natural log of both sides. So taking the natural log of both sides, we should get natural log of t minus t naught divided by c is equal to the natural log of e to the negative kt. And again, the reason we do this is because we want to go ahead and try to get these exponents down out in front. So now that we have the logs, we can go ahead and use our power property to bring those exponents out in front. So that will get us the natural log of t minus t naught divided by c is equal to negative kt, and then the natural log of e. And if you recall, the natural log of e is equal to 1, so we are left with negative kt. So natural log of t minus t naught divided by c is equal to negative kt. And all we need to do now in order to isolate this k is go ahead and divide by a negative t. So divide by a negative t on both sides, and you should be left with just your k. So your k is now equal to the natural log of, in this case, t minus t naught divided by c, and then finally divided by a negative t. Another way you could simplify this is k equal to negative 1 divided by t, natural log of, in this case, t minus t naught divided by a c. Okay, so next we can go ahead and do a solving exponential / log summary. So what you want to do is try to get into one of the forms. So number one, you might have a raised to the f of x, and that's going to be equal to b. The way that you solve that is by taking the log of each side in order to get your exponents down. So you can take the natural log, or you could just take the log of both sides. It doesn't really matter, but you do need to be consistent. Number two, log base a, f of x is equal to b. Solve by changing into exponential form. So again, you have your base, in this case, of an a, and you raise it to your exponential b and set it equal to your f of x. Okay, so next we have our 3 here. So you might have the log base of a, f of x, equal to the log base a, g of x. Basically, you solve this algebraically with applying the property of logarithms. So again, if you have your same bases here, in this case log base of a, you can go ahead and get rid of your logs on both sides, leaving you with f of x is equal to g of x. Now for 4 here, we have e raised to the 2x plus 1 times e raised to the negative 4x, and that's equal to a positive 3e. What you want to do is use your property a to the m times a to the n, and that is going to be equal to a raised to the m plus n. And then you want to go ahead and try to get it into one of the other methods to solve it. Now, the last and final point is going to be 5, which says to make sure to check your proposed solutions in your domain and that they are positive, right? Because again, we don't want any negative arguments for our logs.